final contributed talk for the day. You've got the graveyard shifts, but it's going to be a good talk. So this is Steve Coupland. I've worked with him for a couple of years. Nice to see you again. And you're going to talk about the foundation model work that's going on at OS right now.
Thank you. So I'm Steve. I'm a senior research scientist at OS. I work in the GeoAI team. Our logo looks suspiciously like the TerraWorld logo. TerraWorld, sorry. Just coincidence, nothing to do with each other. Okay, so I'm going to talk about GeoFoundation models and geofingerprinting. So I'll start with the foundation model. So at OS, we're developing our own GeoFoundation model. We've named it GBNet, and this is a model that is trained using diverse imagery. So this is specifically selected imagery from our own in-house aerial photography, so it's 25 centimeter RGBI, the eye is near infrared. This is especially selected using our national geodatabase, so we've got nearly 500 million attributes that we can actually use to select particular areas and locations. So we use that to select very specific parts of imagery that we think are really useful. We then use a self-supervised approach to our model training, and the idea is that it should learn complex representations of features that can be applied to a range of tasks. So on the posters outside, there are a range of tasks that feature all these methods that we've got shown here. Particularly the things of interest for us is semantic segmentation and change detection. As a mapping company, tends to be what we do most often. So, why bother with our own foundation model? As I've said, we've got a lot of AI that feeds into production methods. So, using our foundation model as the sort of backbone of this production, we can actually get a lot better quality using less data. And therefore we can use smaller compute resources, which means we can train the models in less time, and that lowers our emissions overall. And because we're using cloud compute, time is literally money, so reducing the cost as well. The architecture that we use and the method we use is contrastive learning. So this is going to be the most complicated thing to explain. So basically we're selecting imagery using our national geodatabase. The imagery that we're interested in is pairs of data, because we're doing contrastive learning, so it's got to match pairs together. To make our pairs, we're using a SimCLR approach, and we're using pairs of imagery where we're using old and new imagery. And the idea is that we're selecting specific imagery where not a lot of changes happen. So roads are still there, there's no new buildings, there's no major extensions, that sort of thing. We don't care about atmospheric change, we don't care about seasonal change, or the time of day. It's just as long as there's no major changes. So the idea is, as you've seen a few times today, data goes through the model, generates some embeddings based on those features that are present in the data. Then a projection head, in this case, is trying to do the contrastive learning part. So it's trying to bring together pairs of imagery that are similar, and then as we pass more data into the model, as it finds similarities in features and differences in features, it tries to move pairs that are more similar further away from pairs that are more different. That's where the contrasting part comes in. So it can only do this by learning the actual features that are present, so it learns about buildings, roads, solar panels, paths, and so on. So once we've trained our model, we basically want to use it in production. So we can then attach domain-specific projection heads to the model. So essentially here I've got my pre-trained GBNet. I'm just going to take the featuring extractor that creates embeddings and attach a new domain projection head to it, so I can train it as I would do any standard model. So in this case it's training for semantic segmentation, so it's a different domain, but it does basically the same training as any other net. Once we trained our model, we decided we needed to benchmark it, and luckily for us, because we already have models in production, they have gone through a strenuous quality assurance check. So we've got Land Cover, which is the first ever fully AI created product that OS uses. So this is a good starting point to use as a sort of trusted method of testing a benchmark model. So we trained GBNet versus a model that's trained from scratch, and also a model that's using ImageNet. The task is to predict land cover labels as semantic segmentation, and we're running benchmarks in fine-tune and a linear probe scenario. Just to recover what those are. End-to-end fine-tune, we're talking about a model where the encoder and decoder segmentation head is trainable, and for a linear probe, just the projection head is trainable, so a difference of 24 million versus 3 million trainable parameters. So here's some results. We've got GBNet, followed by ImageNet, followed by a completely trained from scratch model. As you can see, GBNet has luckily surpassed the models. We've got a difference of 8 percentage points improvement, but this is an early version of GBNet, so it's only trained with about 50,000 pairs, so this was an early benchmark to make sure we're doing the right thing. We're now scaling this up to a much larger model and a much larger training set. Something of note that we've noticed is that the linear probe approach, it actually surpassed ImageNet's final results in the mean IOU. So we could have actually got the same level of production quality with a lot less data, well, sorry, not a lot less data, a lot less computation power and a lot less time. So it's like a lesson learned for us there. We also looked at the influence of the data, so varying the amount of training data available to the model. So we've got 20,000 patches in total, so we looked at what the impact of having just 1% of the data up to 100% of the data would have on the models. There's some interesting figures here. So at around 20% of the data set, our GBNet model actually surpassed the random initial model. So basically, you'd get the same results if you train from scratch by just using GBNet with 20% of the data. And at a further 35%, that's when we started surpassing weights. So this meant that if we were to do this approach starting from scratch, we could have had 50 to 60% savings in terms of training time and computation efficiency. Here's a check that's less scientific. So we basically, because we passed data through our model and created embeddings, we decided to see what the nearest matching image is based on its embeddings. So we took image A and then said, based on the embeddings, what's the next nearest matching image? So returned this sort of farmland area. But the thing that we're interested in is solar panels in this case. So we wanted to see what would happen if I took the embeddings from image A, took away the embeddings from image B, and then added new embeddings from image C, which is just some rough grassland. Then the new returned result is this area of solar panels in a grassy area that's not farmland. So it shows, in a very unscientific way, that the model has learned something specific about the embeddings related to solar panels that are not just related to the surrounding features as well. So we can extract a bit more meaning. Another check we do is to explore the sort of latent space, so doing dimensionality reduction to see how a model would plot all the sort of embeddings into a 2D space. You can see there's some clustering going on that's quite significant. If I apply some coloring to it, I should add at this point, the guy who did the colouring is colourblind, hence green spaces are blue. We can see some clear clusters that actually make sense with what's in the data. So here we have tidal features, green spaces, and then residential buildings. There are a few outliers, so we've got a few little green spaces which have large bodies of water in, so that's fine. We also noticed that we had this random bit of green spaces where it wasn't quite sure if these are green spaces or are these residential. So we investigated a bit further to see what this grouping is. And it's allotments, which OS says are green spaces. They look kind of like gardens, but they don't have buildings around them. So the model deciding to cluster these made a lot of sense, and it means that we probably are seeing something where significant grouping is actually occurring. Okay, so that's covering the model. Geofingerprinting. So this is where it's going to get very futuristic and speculative and a bit weird. So, traditional machine learning, we all know about. You have thousands of hand-labeled images, you have a mental breakdown after you've made them, you train a model, and then you make some predictions and you hope it's right. It's basically a glorified calculator. The problem is, data can be uninterpretable depending on what it is. In our case, when it came to a model that could predict roof materials, we found that humans are not exactly that good at detecting roof materials themselves for the labeling. So we couldn't tell the difference between asphalt and concrete, we couldn't tell the difference between slate and normal tiles. So we thought, what if we could change this approach to make the model do the hard work, and then we just do the analysis at the end? So the idea of geofingerprinting is to create augmented sets of data based on areas that you know about already, use a self-supervised approach to create unique embeddings or fingerprints, and then use human exploration at the end when you've got simplified representations of your data. So here's an example of that in action. So this is a vision transformer model. We're feeding it augmented versions of roof materials, so 25% of the data is roof materials. The model can only see roof materials, and it has to then try and rebuild the image around what it sees. So it's building like grass based on residential buildings, tiles, that sort of thing. This causes the model to hyper-focus on roof materials only, so that when I pass data through the model that's not augmented, it suddenly has this huge focus on roof materials only. Well, not just only, but mostly on roof materials. So this is an example of how a model sees the data. So and probably, well, if you remember from Anne's presentation, the data goes into the model. There's some sort of pre-encoding that happens. So it's like a dimension reduction or an increase. And then this is what the model sort of sees after that stage. This is then the model's attention layer. So the output is basically bright colours, it's really paying attention to it, and dark colours, in this case red, where it's not really paying that much attention. So it's creating unique embeddings based on roof materials only and not the surrounding features that I don't care about. This can then be, again, analysed by humans, so converted into a reduced space, so 2D representations and clustered. So I could then potentially use my actual surveyors to go out on the ground and say, well, I've got this cluster here. Can you investigate what these actually are in the real world? And then report back to me, and then I can use that as a classification rather than having to do a lot of labeling or a lot of feature extraction myself. And it could uncover a lot of unexpected features as well, because we didn't have any classification for these new like faux roof materials where it's plastic masquerading as slate, or these new solar tiles which actually integrate into roof panels. So there's a lot of unseen data. And that's it.
Thank you very much, Steve. So, I'm sure questions. Does anybody have a this one?
The slide where you had the kind of landscape sort of adding and subtracting, you had a final image C. Was that a generated image that was on the solar panels, or was that an actual landscape?
Oh no, that was an actual one. So it looks a bit weird because it has been edge matched from different frames. So that's why it looks a bit janky. But that is real data.
It's just a question on the training for the GBNet model. So you did contrastive learning between two tiles. You might have said it, I might have missed it. Is it the same geo tile just from two different times?
Yeah, exactly the same location with different times. So we basically only select areas where we've got multiple years of imagery and where there's not been significant change. So it's not like a park in one and a housing estate that's been freshly built. It'll be the same features present in both.
Okay. So for the contrastive loss then, you're specifically telling the model these are similar because they are the same place. Okay. And then you reinforce that with like negative sampling as well? Or?
So essentially you get 1,024 pairs of images per batch, and then you've got to try and separate those. So it's building a very complex set of features. The thing that we need to research a bit further is, do we need to actually curate those sets to make sure that there's no just or something like the same type of groups, because that might cause them to say, well, I think these are the same, but you're saying they're not the same. So that might be something we need to do in the future.
Did you do anything with the pairs of tiles, or when you were training your models to look at trying to learn something that's rotationally invariant, so that if a road is going north to south versus east to west, it still looks like a road in the road in that cluster, or is that just a sort of emergent property?
Yeah, so we're looking into now about how we can actually extract particular layers from the model to see if we can be invariant to rotations of like roads and things. Because yeah, one thing that we did notice is we extracted a very particular layer and did the dimensionality reduction, then direction became quite important. And then if we used layers previous to that, then it wasn't important. So it just depends how we extract that data.
Let Steve sit down. Thank you, Steve.
Thank you.